Welcome, friends, to another video edition of Science Talk. I am your host, Jim Massa. Okay, this topic right here. Late Quaternary abrupt climate change in the tropics and subtropics, the continental signal of THEs, better known as Tropical Hydroclimatic Events. This paper is basically a review paper appearing in the AGU's Review of Geophysics. The authors are Raymond Bradley and Henry Diaz. This is a lengthy paper. I'm going to basically concentrate on certain highlights of it. I will, of course, leave the URL in the comments section below, so those interested can read in further detail the information contained therein. Okay. So the abstract, tropical hydroclimatic events characterized by extreme regional rainfall anomalies were a recurrent feature of marine isotope stages 2 to 4 and involved some of the most abrupt and dramatic climatic changes in the late Quaternary. These anomalies were pervasive throughout the tropics and resulted from the southward displacement of the Hadley circulation, which is an atmospheric, cells typically located between 0 and 30 degrees north-south latitude. So we have the southward displacement of the Hadley circulation, also a southward displacement of the ITCZ, the Intertropical Convergence Zone, and its associated convective rainfall modulated by regional factors. Lake sediments, stalagmites, and offshore marine sediments that integrate inland continental conditions provide a comprehensive record of these changes over the past approximately 70,000 years. Vast areas experienced severe drought, while other areas recorded greatly increased rainfall. Dry areas got drier, wet areas got wetter, basically. Within the uncertainties of dating, these tropical rainfall anomalies occurred very close in time, plus or minus 100 to 1,000 years, to the deposition of North Atlantic ice rafted debris, or IRD, okay, that defines what is known as Heinrich events, HEs. The ice rafted debris record is a good proxy for the amount and distribution of additional freshwater forcing which was necessary to bring about a drastic reduction in the overturn of AMOC, right, Atlantic Meridional Overturning Circulation, strength during each HE. As a consequence of this reduction in AMOC and an abrupt expansion in the area of sea ice, cooling of the North Atlantic and adjacent continents took place with a rapid atmospheric response involving the southward displacement of the ITCZ and associated rainfall belts. The climatic consequences of this large-scale change in the Hadley circulation, modulated by regional factors, is clearly recorded throughout the tropics as a series of abrupt and extreme hydroclimatic events. And they discuss possible physical mechanisms. Hey, plain language summary. Many continental paleoclimate records from the intertropical zone show there were occasional abrupt changes in rainfall across the region that we call tropical hydroclimatic events, THEs. These extraordinary climate changes occurred throughout the tropics with excessive rainfall in some areas, while at the same time other regions experienced severe drought. These events resulted from large outflows of fresh water into the North Atlantic. The sudden freshening of the subpolar North Atlantic led to a slowdown or cessation in deep water formation, AMOC. Right? This led to a rapid reduction in the northward flux of heat by the ocean in the poleward flowing Gulf Stream current, which in turn led to a reorganization of the atmospheric general circulation, modifying the climate in various parts of the world. The consequences of the large and sudden flux of fresh water to the North Atlantic, leading to a collapse of AMOC, caused major rain belts across the tropics to shift southward. But this large-scale atmospheric response had different regional consequences. They go on to say we provide an overview and discuss some possible physical mechanisms. Okay, so we know, and they mentioned Wally Broker in this article, we know from Wally Broker's work that when you input fresh water into the North Atlantic, putting a freshwater lens, diluting the surface salinity, that AMOC can slow or stop, and that in turn leads to a cooling down, at least hemispherically, if not planetary conditions, oftentimes or sometimes leading to the promotion of ice sheets on land, ushering in an ice age. We know that. Of course, nowadays things are different due to all the heat in the water, in the oceans. That's going to modulate things. We're going to, when AMOC, which is slowing down, I expect to see regional cooling, not necessarily hemispheric. However, there is an important lesson out of this. Precipitation patterns will change, right? So that's the lesson, looking at the past, that's the lesson for us now, is that precipitation patterns will change. And we are starting to see that in various regions across the planet. So this is important work here. Okay, so let's look at some of the review here to give a background. The focus of this review is on the climate of tropical, subtropical regions at times when ice-rafted sediments or ice-rafted debris, IRD, were carried into the North Atlantic and deposited over large areas, typically between 40 degrees north and 55 degrees north, in what's called the Rudderman Belt. Around these times, large and abrupt changes in hydroclimate resulting from major changes in rainfall amount distribution where they're taking place were widespread across all low-latitude regions. These changes are distinct from other abrupt changes that are associated with the Dansgaard-Oeschger DO events seen in ice cores. So now they go through some terminology here. Okay, we know that IRD is ice-rafted debris. It's recognized by distinct facies changes in North Atlantic sediment cores. Stratigraphically, these are Heinrich layers. Since these layers appear to have been deposited within a relatively short period of time, probably to coincide with the ice-rafted debris and the freshwater influx, the term Heinrich event, HE, describe these depositional time intervals. However, not all HEs were the same. Some appear to have been abrupt and singular events, for example, HE4. Others had multiple phases. And they refer you to Figure 1, which shows a stack of IRD records from the North Atlantic. And they go on to say they'll use that record throughout the article for comparison purposes. Okay. So, second, for 0 to 40,000 years before present, the dating is based on radiocarbon, whereas dating of the 40 to 150 years ago is by correlation to the Greenland Ice Core 2005 chronology, or GICC05, and the speleothem age modeled interpolated to 1,000-year intervals. Third, only 5 of the selected cores extend back before MIS4, while the timing of maximum IRD deposition in this composite record is fairly clear, defining precisely when the HEs began and when they ended is more difficult. So let's take a look at Figure 1. Let's go through the description first. Okay, North Atlantic ice-rafted debris stacked from 15 sediment cores. Brown shaded range indicates time periods when IRD values exceeded the median value. Right? Here's the median value, this dashed line. We'll look at a large version in a moment. Marine isotope stages indicated at the top, up here. Okay. Note that the timing and magnitude of IRD maxima vary from one location to another. Only 5 cores extend back before MIS4. Okay, and here's a link there if you want to look at the more data. So let's take a look at the figure here. This is thousands of years before present. So the 0 is today and going back 150,000 years. And you can see they identify about 12 of such events. 8 and 9 and 10 were below the median, whereas we see 1, 2, and 4 were probably the strongest Heinrich events. 5, 6, and 7 were fairly decent, but 1 through 7 were all above the median, right? And they put ice rafted debris normalized units. So that's what the mean is. The median is referring to, about 0.13. So that's gives you an idea of when basically there was a lot of ice rafted debris deposition. That's what these represent. High rates of ice rafted debris deposition. And in the table here, they go through a timing of when these occurred. Since Heinrich layers are presumably associated with freshwater forcing, melting icebergs, and icebergs, they carry debris with them and they melt, the debris gets deposited. Hence the term ice rafted debris. It's on land. The analogy would be that glaciers are proceeding along, then as they melt back, they're grinding the ground, and so it's at the bottom, and then when the glaciers melt, all that debris gets deposited right there, and you can usually, geologically identify those depositions. So these layers are presumably associated with freshwater forcing, and such forcing is linked to a reduction in AMOC strength. Some have used the term Heinrich stadial to describe a period of reduced AMOC and associated cooling. But in fact, North Atlantic cooling often preceded the deposition of the ice rafted debris, so use of this term is confusing. Furthermore, a reduction in AMOC leads to warming in the southern hemisphere. It seems illogical to link the word Heinrich to a stadial at all. Okay. In this article, abrupt and significant rainfall changes in the tropics, subtropics are referred to as tropical hydroclimatic events, THEs. We consider the continental records that provide evidence for one or more THEs in MIS 2 through 4. And they go on to say the other records and how they considered. Now let's look at figure 2. Locations mentioned in the text. So we go through a whole bunch of locations there. We can look at it, and as you can see, lots of locations here. So this is the equator, of course. This is 30 degrees north, 30 degrees south, referring to, of course, the Tropic of Cancer and Capricorn. Tropic Cancer, Tropic Capricorn. And these basically will be prominent in this article, as a lot of these sites here are referenced in the text. Controls on tropical, subtropical climate. The climate of the tropics and subtropics is dominated by the Hadley circulation, which creates distinct seasonal changes and strong regional variations in rainfall related to passage of the sun overhead during basically the equinoctial seasons, March, September. The Hadley circulation has two distinct cells, with the ascending limb, the intertropical convergence zone, positioned slightly north of the equator today on average, and areas of subsidence to the north and south in the subtropics. However, in the solstitial seasons, June, December, there is only one cell, with the area of low-level convergence and rising air shifting from north of the equator in boreal summer to south of the equator in boreal winter, with a corresponding hemispheric shift in the zone of subsidence. Net heat transport is oriented in the direction of motion in the upper branch of the Hadley cell, where moist static energy exceeds that at the surface. Thus, energy is transported away from the ITCZ. So when the ITCZ is displaced towards the southern hemisphere in austral summer, boreal winter, there is a northward transfer of atmospheric energy across the equator. And when the ITCZ is in the northern hemisphere, boreal summer, austral winter, there is a southward transfer of atmospheric energy across the equator. So basically, we have an oscillatory thing going on here, is what they're saying. It's shifting back and forth. That's how you sum that up. There's an oscillation going on. And we actually might see part of that signal in the interdecadal Pacific oscillation, which involves the ITCZ. I did a video discussing the interdecadal Pacific oscillation combined with the Pacific decadal oscillation, which involves the northern Pacific. You might want to check out that video. Today, because of the oceanic transport of energy into the northern hemisphere via the AMOC, well, that's a little confusing there, and we need to clarify that. What happens is you form the deep water sinks. As it sinks, it pulls the Gulf Stream up towards the north. If AMOC slows or stops, the pulling of the Gulf Stream northwards is going to slow or stop. So they're making it sound like AMOC is deliberately pulling the energy when it's really AMOC is pulling the Gulf Stream, and the Gulf Stream contains the energy that is brought into higher latitudes. And we know that the northern hemisphere is generally warmer than the southern hemisphere, so that the mean position of the ITCZ is slightly north of the equator, which leads to a compensating net flux of atmospheric energy into the southern hemisphere. It follows that a reduction in the oceanic flux of energy to the northern hemisphere would result in a southward shift in the mean position of the ITCZ, such that the net atmospheric energy flux would then be from the southern to the northern hemisphere. Thus, the magnitude of the overall ITCZ displacement latitudinally would depend on the interhemispheric temperature difference. Right? Let's highlight that. Important statement right there. The magnitude of the overall ITCZ displacement would depend on the interhemispheric temperature difference. Figure 3 kind of tries to model this for us. Take a look at it. Zonally average wind in meters per second, easterly winds are shaded, and mass stream function, mean flow with height and latitude, 10 to the 10 kilograms per second, for 4 seasons shown with respect to latitude and altitude. And the pressure is measured in HPA, pascals, right? So, let's look at the figure here. So JJA, that's June, July, August, zonal wind, okay, meters per second. You can clearly see, and this is north latitude, south latitude. Right here, you can clearly see the Hadley cells. There they are right there. You can clearly see that. Okay? And here's the stream function. And you can see that we have the rising transports across with the convective rainfall coming down. So here we see we're moving the heat to the southern hemisphere and it's coming down in rain. Now, December, January, February, I still have the Hadley cells here, but now look what happens here. We see how it flips. Now, here we have the heat going to the southern hemisphere, and then it comes down as rain. Now we have the heat going from the southern to the northern hemisphere, coming down as rain. It flips. Totally flips. And then we have March, April, May, and this is September, October, November. And you now notice what? That there are two cells. This is what they're referring to with the two cells during the equinoxes and the one cell during the solstices. We have the two cells here, and basically bringing heat to both sides. And you have to you have to calculate the energy to see, and that's what they did to make the statements that they said with the net flux going from one hemisphere to the other. We see that right here. You got the two cells. So it's a nice little diagram showing what's happening. Basically, I consider this figure an important one that sums up this entire discussion. Figure 4 illustrates the consequences of seasonal changes in the Hadley circulation today in terms of zonal mean rainfall distribution. The convective rainfall belt is confined to a narrow belt over oceanic regions and varies little throughout the year, whereas over continental areas where you find large seasonal changes in surface heating taking place, heavy amounts of summer rainfall extend far from the equatorial ITCZ, illustrated in Figure 5. Regions with large seasonal changes in rainfall are commonly described as having a monsoon rainfall regime. Regional variations due to the distribution of the continents and seasonal changes in circulation create sharp boundaries, both terms of geographically, temporally, time, between areas with a high convective rainfall climate regime and much drier areas where warm subsiding air is dominant. Now let's give you the zonal mean rainfall distribution over the oceans. That's up here. And over the continental regions, that's down here. Okay. So again, June, July, August, December, January, February. And you can clearly see, this is the oceans up here. And this is the continents down here. You can see that the amounts are higher. It's over a wider band. Right? Take a look at the narrow bands here, and you got the wider bands here. And they give you precipitation rate that's meters per year. That's 3 meters per year. That's 10 feet. That's a wee bit of wet stuff. You can see it's over the southern hemisphere. What is interesting to note is that in June, July, August, where it falls does not really change all that much. But look at December, January, February. There is a noticeable switch from north of the equator to south of the equator over the land, over the continent. That's a noticeable shift there. Now here's Figure 5. January and July, boreal winter summer, rainfall totals and position of the ITCZ. Black dotted lines indicate the ITCZ location in the opposing season. Red lines denote the equator and Tropics of Cancer and Capricorn. Okay. So let's take a look at this. Enlargement, please. There we go. Okay, ITCZ, Intertropical Convergence Zone. They give you the latitudes here. This is winter. This is summer. Take a look what's going on in winter here. Okay, we see it pretty much between zero, it looks like about maybe 10, 15 degrees north latitude, down to about, say, 25 degrees south latitude. But in the summertime, this is a pretty big shift here. We're going from basically, say, 10 degrees, maybe 15 degrees south latitude to basically, in some places, well above 30 degrees north latitude. So we see a definite shift in the precipitation when it occurs. And also take a look at what the ITCZ is doing. Kind of a flip flop. Right? Look at that dash line. Look at that dash line. They basically change positions. Equator, right, and the two tropics. So we see that. Also note in summertime in the eastern Pacific off the western coast of the Americas, we have a little more intense rain falling. Now, then we probably need to look at what stage of the ENSO cycle this takes place in. But we can see some dramatic changes. We even see some dramatic changes in located with the gyres in the Pacific and the Atlantic Ocean. Notice, though, the increased rainfall over, or whatever precipitation over South America in wintertime. And it reduces greatly in the summertime. So in wintertime here, right, versus the summertime here. Now, technically, if this is the southern hemisphere, this same summer is July. Well, July would be winter in the southern hemisphere, and January would be summer in the southern hemisphere. So what we're seeing is that there's more rainfall in the summertime for both hemispheres. And they go on to say that the distribution of rainfall during the northern and southern summer months, when surface heating is greatest, is influenced by the extent of land area, topography, mountains, that kind of stuff, and other factors in each continental region, as well as the specific humidity of air entering into convective plumes, which transfer moist static energy. Okay. The delivery of moist air masses to continental interiors via trade wind monsoonal system is closely linked to upwind sea surface temperatures and wind strength. The distribution and amount of rainfall therefore depends on a combination of large-scale circulation dynamics, Hadley circulation, oceanic surface currents, and local thermodynamics, which varies regionally. Okay. And they go on to look at a couple of examples. The signal of the THEs in the Americas. And this is a very lengthy section. They go through like Florida, the Bahamas, and the Caribbean, and they do a deep dive. They get into the weeds, and explaining possible what the data is going on, possible reasons for the data. The stalagmite record provides strong evidence that sea surface temperatures were average cooler. Now they 4.3 plus or minus 2.7 Celsius than present, with oxygen isotope maxima at 15, about 24.1 and 31.5 thousand years before present. So they look at that, and they present the figure here. Oxygen isotope record. So from Santo Tomas Cave in Cuba and Cueva Larga, Puerto Rico in red. So Cuba is the black and Puerto Rico is the red. Dash blue lines, that's these vertical guys, indicate the timing of maximum ice rafted debris. So let's take a little enlarged look at that. So we see the Del 18 oxygen isotope record. So positive is this way, negative is that way. And what that tells us is that the fraction of O18 has increased when it's positive and decreased when it's negative. In other words, you've got more ice that is present. So because then the water is locked up in the ice, the water usually contains more O16, so leaving the O18 behind, that would then show up in the signals, and vice versa. So as we can see here, when we have maximum ice rafting debris here, we tend to have positive del 18 oxygen levels. We see it here, a little bit there, but definitely here in THE3, and THE5 doesn't quite line up, but it's kind of, this is where they talked about sometimes it preceded. Here's an example of that. A little bit of preceding right there, slight preceding there. So you can understand why they say that in the text. But still, it's some very interesting data. They do the same thing with Central America. And they go through Central America, and again, they present the data. And I look at carbon isotope from Lake Petén Itza, Guatemala, based on ostracod species. Dashed blue lines indicate the time and the maximum IRD, etc. So let's take a look at that. Shaded brown areas indicate when the IRD exceeded median values. Now looking at the Del 13C. And when we have the maximums here, THE1 and THE4 show some interesting results here. We get closer to the maximum, we see a reduction in the Del C13. Now, recall that when I did my isotopic fractionation video, oftentimes we looked at the fractionation of carbon to tell, along with the oxygen as well, when the conveyor belt was running or not. If you have a less C13, that typically means you've got the conveyor belt is slowing down because the plants are not, because the plants have taken up more of it. So I don't think this data really shows much correlation just looking at this, but still, they present it here. There's one good correlation here. I'm not so sure about the rest of it. Maybe THE2. I'm not sure about the rest of it, but generally speaking, we can use the 13 fractionation along with the oxygen fractionation to draw a conclusion as to if the conveyor belt is running or not. And what they're basically saying is if you have these THE events along with the HE events, the Heinrich events, it's kind of redundant there, but associated with the ice rafting debris maximum, that would lead to a cooler situation in the northern hemisphere, warmer situation just south of the equator, and therefore this is enough to change the precipitation pattern. That's the essence of what they're trying to demonstrate in this paper. So keep in mind, when we see these IRD maximum, that we have cooler conditions in the northern hemisphere. Then they decide to look at pollen record from the Americas, and they look examining what's going on in Sabana de Bogota in Colombia, where a subsiding basin has preserved a record of environmental changes spanning the Quaternary. Vegetation in the area is zoned altitudinally, ranging from tropical forest below 1,000 meters or so to Andean forest above 2,300 meters or so, and then to Paramo, which is above 3,500 meters. That's getting up there in altitude. Pollen has been analyzed throughout the period of record, but in remarkable detail, about a 60-year resolution for the last 284,000 years, given a very good detailed paleoclimatic reconstruction from the tropics. Okay. And They say pollen day is more difficult to quantify in terms of hydroclimate, but during HE1 and HE3 to 6, the area was relatively wet. Evidence is less clear for HE2, definitely was colder. They did not include a figure for this. I would have liked to seen a figure for that. Okay, so we're looking at the South America here. They look at off the coast of Venezuela, anoxic conditions result from high surface productivity, restricted circulation due to a shallow sill separates the basin from the open ocean. This unusual condition leads to the preservation of sediments with minimal bioturbation, basically pretty much left alone, at depths below 300 meters, alternating between light-colored foram and silica-rich sediments and darker sediments rich in organic carbon. These different facies reflect large-scale circulation changes. When the ITCZ migrates far to the south, northeasterly trade winds leads to an upwelling of cool, nutrient-rich waters. As the ITCZ migrates northward, heavy convective rainfall leads to a surge in runoff from rivers draining into the Caribbean from the northern coasts of South America, with an increase in minerogenic material, organic carbon, from the continent. Changes in the dominant mode of deposition can be seen in the total color reflectance, or lightness, which therefore provides an index of the prevailing circulation regime, as well as the relative position of the ITCZ in the region. So the Cariaco Basin reflectance, L star, is highly correlated with isotopic changes in Greenland on the millennial timescale. So basically, we see here periods of foran-rich reflective sediments are also period at the time of certain HEs. By analogy, the seasonal changes in sediment deposition, these events were associated with strong upwelling. So what we see, and we'll look at this figure in a bit, where we see high values, we had upwellings. And that means we have a high reflectance, we have more forams versus carbon material being deposited. They also look at elemental iron when it has low values during some of the HEs. According to them, this indicates little runoff from South America at those times and thus low rainfall amounts over the river catchments. So we have the reflectance here. And we see high values there. So that would indicate upwellings. And it seems to sort of correlate nicely with the THE events. They seem to track when there's a peak here in the red value, it seems to track with the black values there. So we got the high reflectance indicating forams, upwelling, and upwellings down off South America, but cooler conditions in the northern hemisphere. Sediment cores off the coast of northern Peru, so look at Ecuador and Peru now, about 4 degrees south, provide a record of terrestrial runoff spanning at least 18,000 years. Ti to calcium elemental ratios reflect dilution of the carbonate fraction due to high amounts of sediment transported into coastal waters. Increased sediment flux occurred during THE1, about 18,000 years before present, with a minor increase during the Younger Dryas. That's basically referring to this section here. Again, maximum IRD. You can see that the THEs and the HEs are kind of lining up with, and they typically maybe, even with just a little bit of a lag or lead time, whatever, are pretty much lining up with the ice rafted debris maxima. In the Andes of central Peru, cave stalagmites record generally higher rainfall, stronger South American monsoon, at the time of HEs, particularly 3 and 4, though the signal is complicated by considerable millennial scale variability. Further east on the Amazonian side of the Andes, stalagmites also record higher rainfall at the time of most North Atlantic HEs. So again, let's now look at this. Stalagmite 018 records from Cueva del Diamante in blue and El Condor in red. So let's look at that. There's the Del 18 there. Here are the years before present. Again, each of these brown areas is this is the blue dashed line, the maximum IRDs. This is kind of the HEs, the THEs when they occur. And what we're seeing here is that, at least looking at the stalagmites, and this is basically, all the values here are negative. It's just that up on top is less negative. So it gets more negative, at least the oxygens in the stalagmites found on the Amazonian side, and they seem to be lining up with, for the most part, with when the THEs take place. So blue is the Diamante and red is the El Condor caves. So they almost seem to be going, at least over here. Well, it does drop down. So we do see they do pretty much track, at least through THE4, they do pretty much track closely. It seems around THE5, it kind of falls apart a little bit, and that must be those other factors that they alluded to in the text. And then figure 10, composite oxygen isotope record in 4 stalagmites. We use different colors. From Santiago Cave in eastern Ecuador, more negative values indicate wetter conditions. Okay. More negative values. Wetter, wetter. And it seems to be lining up with the THE events. Telling us that the ITCZ shifted, the Hadley cell shifted, it affected rainfall. Then we move on to Bolivia. Here they looked at gamma radiation, which is a proxy for effective moisture in sediment cores from Salar de Uyuni. The gamma radiation is a result of the radioactive decay of potassium, uranium, and thorium, elements that are more concentrated in the lacustrine muds than in salt deposits. Higher values are indicative of wetter conditions. Millennial scale increases in rainfall are superimposed on low frequency changes driven by precessional forcing. Fancy way of saying, let's look at the Milankovitch cycles. So, higher values indicative of wetter conditions. These would be higher values. And once again, that one doesn't quite line up, but for the most part, it sure does. So basically what they're doing is they're presenting the data in all its extreme detail to make the point that when you have changes in the Atlantic meridional overturned circulation, it changes the ITCZ, it changes the Hadley cell, it affects and changes the precipitation patterns, the amounts, where it falls, it shifts that around. It precipitates in a heavier manner, i.e. more precipitation. And they're presenting the data that shows this. That's what they're doing here. And they move on to Brazil. I said, you can pull up provide the link. You want to read this in detail, go for it. I'm just presenting to you basic data and with the basic message of what this is all telling us and how we can take this information and apply it to today's situations. Now, they do note that wetter conditions during HEs were clearly recorded further south and eastern Brazil by periods of stalagmite growths in caves that were too dry for such calcite deposition at other times. They then say isotopically depleted rainfall from the Amazon basin reached the southernmost parts of Brazil, and this is due to the extreme southward displacement of the ITCZ and associated convective rainfall. Go back to this figure right here. This helps explain. This is the figure that kind of drives a lot of the discussion in this paper. So once again, to look at the ratio, and we see that THE 1, 3, 4, little miss on 5, 6, pretty much line up. This is interesting. A peak in between the THEs. This is also interesting. And by the way, if you look at this, these THEs do appear to be somewhat periodic. Like maybe 10, 15,000 years or so. I mean, that's about 8,000 years. That's about maybe 6 or so. It's about 10. Appears to be periodic. Think about that. Think about the periodicity of the ice sheets growing and receding. Then they move over to Africa. And they look at the iron to potassium ratio in sediment cores. Higher values of the iron potassium indicate wetter condition, as the more weathered rocks in humid tropical regions contain more iron relative to the more mobile potassium. Low values that punctuate this record thus indicate much drier conditions in the continental interior, as the ITCZ and associated rain belts shift southward, and the trade winds deliver dust from the arid interior of the Western Sahara. And the gray areas at the timing of the HEs. So, what do they say here? Higher values indicate wetter conditions. So we have dry conditions, dry conditions, dry conditions. The wet conditions appeared not to be associated with the HEs because of all the various factors that they are explaining. Now let's say, moving further south along the coast of the Gulf of Guinea, the Del 18 oxygen foreruns record changes in sea surface salinity, which is affected by variations in river flow, isotopic composition of rainfall, as well as what's happening with ice sheets or not. More enriched isotopic values are clearly seen during North Atlantic Heinrich intervals, indicating reduced runoff and or heavier isotopic values of the rainfall entering river systems. Notice it contains more oxygen 18, which might be expected with a reduction in monsoon convective rainfall, as there is no evidence that the ITCZ was displaced to the south of the east-west trending West African coastline. This suggests that the seasonal migration of the tropical rain belt was greatly reduced during Heinrich intervals. And to say today, maximum rainfall occurs in about the 5 to 10 degrees south latitude of the zone of surface wind convergence. So let's take a look at this figure. Monthly mean precipitation in millimeters per day and 10-meter winds from the ERA interim reanalysis. Black lines illustrate the main zone of the ITCZ, which is generally north of the rainfall maximum. Dashed black lines illustrate the Congo air boundary. Red lines the equator and the tropics. So as we can see here, and just to orientate themselves. So this is the African continent, right? Rift Valley over here. As we can see, where we see the green, I guess brownish colors, whatever, that's the increased precipitation, millimeters per day. January, uh, I guess they go vertical. January, April, July, October. Okay? Keep in mind, in the southern hemisphere, January is their summer. So April is their autumn, July is their winter, and October is their spring. And you can see how it shifts around. You can also see how the ITCZ moves around. I mean, there's some pretty dramatic shifts there. You know, we see it starting to creep up northwards until it reaches basically 30 degrees north latitude, and then it starts migrating back down south to nearly the equator. So we see those shifts there. So, in summary, offshore sediment records from the tropical subtropical regions of West Africa provide a clear picture of reduced rainfall throughout the region during Heinrich intervals, with a strong increase in dust flux to the Atlantic within the northeast trade wind. And that's an important thing, by the way. Let me take a few moments to briefly talk about that. You got the winds blowing across Africa, and they go in an east to west direction. And they pick up the dust there. We actually call that aeolian transport, and it might have kaolinite types of material in it, and we see, and it gets deposited. It gets deposited in the ocean. It gets deposited in North America. So we can see that, and we can track the rate of deposition, how that changes over time, and that gives us a clue as to the strength of the winds and where the winds were precisely which direction they were blowing, what the actual vectors of it are. So they're basically saying that if you got reduced rainfall, that means you have an increase in the amount of dust being blown around. That's basically what they're saying. And they talk about the southern boreal winter limit of the rain belt appears to remain around 5 degrees north, but the northern boreal summer limit was more restricted. South of the ITCZ, a cooler land area, weaker trade winds led to less convective precipitation, lower rainfall totals. This picture is consistent with model simulation in which freshwater forcing is imposed in the North Atlantic to slow down AMOC. Hosing experiment. A reduction in AMOC leads to a southward shift in the summer northernmost position of the West African monsoon trough, ITCZ, by up to 4 to 5 degrees latitude, and much drier conditions over the southern Sahara and Sahel, with a strengthening of the African easterly jet stream and more dust advected offshore. Warming of the southern hemisphere associated with a reduction of AMOC would also lead to poleward migration of the subantarctic westerlies and a reduction in the strength of the southeast trade wind, contributing to less rainfall. So they're looking at all these data from all over the place and how it's affecting what happens in eastern, western South America, eastern South America, the Caribbean, the western side of Africa as well, and they basically are able to tie this all in as to what's happening with AMOC and how that is affecting the Hadley cells and how that's affecting the ITCZ, it moving things around, and that all impacts the precipitation pattern, the amount of precipitation, and where it takes place. Okay, so then they go on to talk about continental proxy records of climatic conditions during Heinrich intervals are mainly provided by lake sediments, but records that extend beyond THE1 are rare. And they go on to proceed from there. And then now they talk about the signal of the THEs in Arabia and the Arabian Sea. I indicate like the Rift area, Rift Valley area. Well, that's the region they're talking about there. And they're limited in data there. But once again, they looked at the color reflectance index. Lower values are darker, organic rich. Higher values correspond to periods of high levels of terrigenous sediment input. So this is probably more of the terrestrial component there as well. Once again, we see almost a cyclical aspect through the data. So switching, when the values are lower, it's more organic material. When it's higher, from other sources. Then they look at India. Less negative values signify monsoon failures. Okay. Looking again at Del 18. So we can see that here. Monsoon failures means the monsoon basically stopped or slowed down dramatically. Less negative values seem to line up with the THEs. And then they go on to talk about China, Southeast Asia, Northern Australia. The seasonal migration in the ITCZ is greatest over Southeast Asia and southern China, producing a strong seasonal cycle convective monsoon rainfall. Over southern China, air masses associated with the Indian monsoon brings moisture from the southwest. Moist air from the Pacific also enters the region from the east and southeast. Later in the summer months, East Asian monsoon as the locus of maximum rainfall shifts northward. However, by far the main source of moisture for monsoon rainfall over most of southern central China is the Indian monsoon. They talk about how they're finding recent data, which is enabling them to fill in some of the missing information to help reconstruct. Now they got the composite Del 18 record from the Sanbayo Cave, central China. Weak monsoon episodes are indicated in THEs 1 through 7. You can see it right here. 1, 2, right? So we have weak monsoon episodes. Let's move into the discussion here. THE is characterized by extreme regional rainfall anomalies where a recurrent feature of marine isotope stages 2 to 4 involves some of the most abrupt and dramatic changes in the Lake Quaternary climate system. Some areas became exceptionally dry, while at the same time, other regions became unusually wet. We'll look at figure 21 in a moment. Such changes often occurred within a few decades and must have had significant consequences for many ecosystems, forcing a migration of some species in order to stay within suitable habitat. This could lead to localized extinction events. A summary figure showing the areas where increased rainfall was recorded during the THEs. They're in yellow. Areas where rainfall was reduced, shown in white. The modern seasonal range of the ITCZ is shown by the dashed line. That's these guys here. Note that not all the THEs are represented by proxies to the location shown. Individual THEs may have varied in amplitude and duration, as discussed in the text. That's getting into the wonky details. So let's take a look at that. All the stuff in yellow, increased rainfall. All the stuff, white numbers, decreased rainfall, even dry areas. And you can see what the intertropical convergence zone is doing. White as rain appears to be in the Indian Ocean. So we see that sudden shiftward of increased precipitation. It has long been accepted that a large increase of fresh water in areas of the North Atlantic where convective overturning occurs would increase the stability of the water column and reduce the AMOC, an idea first expounded by Broker. Yay, Wally. Okay. Basically, increase the stability of the water column. Translation, stratification. No ventilation, no vertical flow, no sequestration of heat CO2 and other materials from the surface to deeper locations. Where the fresh water might have come from and why remains uncertain. Well, if you've got freshwater lens input from melting Greenland's ice, that's one possibility. It could have increased rainfall for whatever reasons. And we offer no commentary on that. Translation. We ain't going to touch that one. But the connection between ice-rafted debris, HEs, freshwater forcing, AMOC stability is critically important for our discussion of changes in tropical circulation, particularly the trajectory and ultimate distribution of freshwater in the North Atlantic. In this review, we have often associated THEs with HEs, but the challenges of precisely dating marine sediments make it difficult to determine the exact sequence of events which may have transpired over a century or less. Now, of course, in the geological terms, a century or less is a blink. And they go on to say other. More precise data is constrained by issues of bioturbation, etc., etc. And they go on to this, they continue to discuss some of the difficulties, some of the problems with really trying to pin down, to increase the precision and the accuracy of what they're doing and to really try and get the timing down. But even so, within the uncertainties of dating, tropical rainfall anomalies occurred very close in time to the deposition of North Atlantic ice-rafted debris. So basically, and they cite a number of studies, all kind of arriving at the same conclusions. So they go on to talk about other possibilities. The ice-rafted debris record is, in fact, a good proxy for the amount and distribution of the additional freshwater forcing that was necessary to bring about a drastic reduction in AMOC strength during each Heinrich event. The freshwater associated with ice-rafted debris pushed AMOC enough so that it slowed down or stopped. So when that happened, cooling of the North Atlantic and adjacent continents took place. But models looking at energy flux suggest this was alone was insufficient to account for the observed temperature changes around the margin of the North Atlantic. Several studies argue that the magnitude of cooling must have involved a sudden expansion of sea ice, especially in winter. This then led to a rapid atmospheric response involving the southward displacement of the ITCZ and associated THEs, right? The hydroclimatic event, thermal hydroclimatic events. Basically, what that says is, okay, we're cooling down the northern hemisphere, and then we're displacing the heat because it can't be transported northward. So the heat now stays at lower latitudes, spilling over to the southern hemisphere, and then that changes the ITCZ, the Hadley cell, it changes the precipitation patterns. So figure 22 here looks at the pH of the 230 thorium, I think it's palladium, in several North Atlantic sediment cores, values greater than 0.093, that would be below this dashed line, we'll enlarge it in a moment, represent a complete cessation of AMOC. Okay, so let's take a look at it. So basically, anything below this dashed line, AMOC was not running. That looks like about 37,000 years ago and about 46 to 49,000 years ago with a little blip at about 55,000 years ago. High-resolution ice core records of CH4 and CO2 show abrupt increases in these gases over the course of Heinrich Event 145, which may have resulted from wetland expansion over land areas in the southern hemisphere where rainfall greatly increased. These data provide important additional constraints on the timing and duration of the THEs in the tropics. Now, we all know what's going on with the permafrost. We all know the increase of methane and nitrous oxide being put into the atmosphere. Well, also there's another source of methane, and that's from the biogenic processes that take place not just in the permafrost but also in the Amazonian region. The decaying all that material there. That's also adding methane to that. So if we've got an increase of methane, CO2 occurring at these events here, the Heinrich events, is it possible that this could contribute to at least a regional warming? I put that out there for folks to ponder. It is important to recognize that abrupt hydroclimatic changes in the tropics and subtropics were superimposed on low-frequency climate fluctuations resulting from precessional forcing, which strongly modulates rainfall in those regions on timescales about 10,000 to 100,000 years. This may have led to a somewhat different response to freshwater forcing over MIS 2 to 4, depending on the phase of the precessional cycle at the time. What they are referring to is Milankovitch and the 10,000 to 100,000 year cycle. The eccentricity of Earth's orbit changes over about 100,000 years. Precessional, that means when the equinoxes and the solstices occur, where they occur in the orbit, is typically about a 40,000 year cycle, thereabouts. So they are referring to Milankovitch forcings here. In addition, the growth of continental ice sheets affected the global atmospheric circulation. In some areas, particularly Southeast Asia, the extent of continental land area exposed due to sea level changed significantly, affecting both ocean circulation, regional atmospheric dynamics. The effect of freshwater disruptions to AMOC thus played out on a moving target in both time and space. Changes in precession lead to an overall latitudinal expansion or contraction of the tropical rainfall belt, particularly over oceanic regions. That's a reference to this. Get the wider belt here, narrow belt here, kind of what they're alluding to there. Numerous global climate model simulations have examined the tropical response to impose freshwater forcing in North Atlantic. And they list a bunch of references there. Although it's been pointed out that most of these studies place freshwater in the location of the North Atlantic, probably not affected by drainage from the Laurentide ice sheet. They commonly impose volumes of freshwater that are unrealistic in magnitude. Don't know about that. And nevertheless, they provide some insight into the consequences and temporal evolution of a slowdown or complete shutdown of AMOC, regardless of the actual cause. All simulations involving freshwater forcing produce cooling across the northern hemisphere. A southward shift in the ITCZ, associated rainfall, slight increase in mean air temperature over the southern hemisphere. Regional details will vary. Lower temperatures lead to high pressure anomalies over continental areas, which reduce monsoon airflow from the tropical oceans. In addition, there's less convective activity over the cooler northern continental tropics, and so rainfall amounts are reduced. Several authors have noted that ocean heat transport into the North Atlantic is far less than that transported by the atmosphere. Well, I might have a little disagreement with that statement, considering that the Gulf Stream, by the time it gets past Newfoundland, is flowing at the rate of about 150 teardrops. That is bringing an enormous amount of heat. I've done papers with you showing how much heat is being brought up to higher latitudes. So I'm going to disagree there. And they go on to say, a massive expansion of winter sea ice cover due to reduction in ocean heat flux must have been associated with a slowdown in AMOC. They've got that backwards, because if you got ice, you forming the sea ice, you got brine rejection, you're going to increase salinity, you're going to promote AMOC. It's when you put the freshwater lens, which means a reduction in sea ice cover. So they got that backwards. Now, it's true that if you expand the sea ice, you're going to increase albedo, which means you reduce the temperatures. That is correct. Okay? And I've discussed this with you before, how open waters, you absorb more heat in the Arctic Ocean, along with the influx of heat from the currents that they seem to be dismissive of, is leading to sea ice decline. So they continue on. In summary, let's look at the summary and we'll wrap this up here. In summary, a wide range of continental paleoclimate records from the intertropical zone provides a vivid picture of extraordinary hydroclimatic changes that occurred abruptly as the major areas of convection and subsidence across the region shifted in response to a disruption in AMOC. The atmospheric response was swift and global in scale, resulting in significant hydroclimatic consequences across half of the Earth's surface. Given their rapidity, these changes may have been far more consequential for the flora and fauna of the affected region than the long-term changes resulting from the growth and decay of ice sheets. Okay, now, to sum up in general terms here, you change what happens in AMOC, you affect the atmospheric cells, you affect the location ITCZ, you affect where precipitation falls, the amount that falls, and so on. So you're basically changing things around. These changes appear to happen rapidly. What are the lessons from this to what is going on in the world today? Changes can happen rapidly. And if you look at things, we're starting to see examples of this right the hell now. We are seeing examples of rapid changes in temperature, precipitation pattern. Dry areas are getting drier, wet areas are getting wetter, which they basically what they're implying here in a lot of the data they present. And we're seeing the AMOC slowdown. But what is the big difference? The big difference is how much heat we put into the system, how much heat is in the ocean, and that instead of AMOC slowing down, creating a hemispheric cooling, is today probably more regional cooling. We are by putting all this heat in the system, we are changing the jet streams. We're seeing that now, which means we are changing the airflow. We are changing what the atmospheric cells will do. We are changing, therefore, the precipitation pattern. We are changing all of that. And we know by looking at the past, we can take those lessons and apply them to today, and we're seeing this all play out. So this is a very detailed study that presents a lot of information. I mean, if I was to really go into real detail with this, it would be probably 4, 90-minute videos. Well, I'm not going to be doing that. So, as I said, I will leave the URL for those who do want to read this in detail and study this in detail. I'm presenting basically an overview with the major take-home message of that. What they demonstrated to have taken place in the past, we are seeing take place right now. You've heard me say it before. Want to get an idea of what the future will bring? Look to the past. This is another example of that. So I thank you for your patience. I thank you for bearing with me during this presentation. Hope you found it interesting. And until next time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.